In previous lectures, we've discussed the fact that computers use binary for representing data. In fact, when you enter that URL in your web browser, those characters are actually converted to a string of binary digits. What is binary numbering, and how is it used to represent data? That is our question for this video. There are a number of excellent videos on YouTube on binary numbering, some of which are downright entertaining. I would encourage you to take a look at some of them after we finish. In this video, we will see how binary numbers are used. The left side shows decimal digits and the right side shows binary digits. As humans, we've grown up using the decimal system, probably because we were blessed with 10 fingers. However, that is not the only numbering system around. The binary system uses 2 digits, 0 and 1, as you can see here. The decimal system uses 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. In the binary system, a single binary digit is referred to as a bit. Now, I don't really know what you call a decimal digit, but if we call a binary digit a bit, we'll call it, for our purposes, a dit, a decimal digit, a dit. As I've already said, there are 10 of those, 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. Now don't go around telling everyone you see that a decimal digit is a dit because I just made that up. It does make sense though, doesn't it? Other than the fact that the two systems have a different number of digits, binary with 2 and decimal with 10, they work exactly the same way. Now, because we have always used the decimal system and it's second nature to us, most of us have never even considered how it works. In fact, it works just like the binary system. Let me ask you this. What is the value of that dit right there? Would you say 5? What if I suggested to you that the answer to that question is, it depends? Let's take a look at a couple of examples of numbers using the 5 dit. Here's 5,930. That 5 has a value of 5,000. That 5 has a value of 500. This 5 in 59 has a value of 50. And finally, we found a 5 that actually has a value of 5. So you see, a dit's value will depend not only on its own digit value, but also on its position in the number. So what is the value of the position? In both the decimal system and the binary system, reading from right to left, the first position has a value of 1. See, there's 1 in this first bit, and here's 1 in this first dit. By the way, the rightmost digit is referred to in computers as the least significant bit. Our mathematician friends have an expression to explain how the values of the positions change as we move to the left. But let's put it this way. How many digits are there in the decimal system? There are 10. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So, as we move to the left, the value of each position is 10 times greater than the position in front of it. So we see the first position has a value of 1. And then 10 times 1 is 10, which is the value of the second position. And then 10 times 10 is 100, which is the value of the third position. And then 10 times 100 is 1,000, which gives you the value of the fourth position, and so on. It's really simple, isn't it? Okay, so now that we know what we've been doing in decimal all our lives, let's look at binary. The truth is that we already know binary as well because it works the same way. The only difference between the two is that instead of 10 digits or bits, there are only 2. The value of the first position, or the least significant bit, is still 1. But the value of the next position is 2 times 1 is 2, then 2 times 2 is 4, then 2 times 4 is 8, then 2 times 8 is 16, 2 times 16 32, 64, 128 as you proceed on. So you see it works the same way. Notice that I displayed 8 bits. That's because to represent data with the most common coding system in binary, the smallest unit of useful data requires 8 bits. By the way, 8 bits in computer jargon is called a byte, B-Y-T-E. Note that a byte is some combination of 8 zeros and ones. There are many combinations of those bits that can be used in the Ascii coding system, for example, to represent data. A byte, for example, could represent a single alphabetic character such as a capital A or a capital T. In fact, the combination of bits that we see here is a capital A. And a lowercase a has a different combination of bits. Capital A, 1, a bunch of zeros, 1, a 0. Lowercase a, 1, one less 0, and 2 ones and a 0. So a bit is a single 0 or 1, and a byte is 8 of those. A kilobyte is 1,000 bytes. A megabyte is 1,000,000 bytes. A gigabyte is 1,000,000,000 bytes, and a terabyte is 1,000,000,000,000 bytes. You might ask, why do computers use binary instead of decimal? The answer to that is that computers function by representing data with switches that are either turned off, which is represented by 0, or turned on, represented by 1. Modern computers could operate using decimal, but doing so would be much more difficult. A decimal computer would require more than just determining if the switch is on or off. It would need to determine at which position the switch is set from one of 10 different choices. There is nothing easier electronically than determining if a switch is on or off, but determining the value of each switch from a range of 10 values is another matter. At first glance, we might think that decimal is much easier because if we set the bits to their highest value, we can represent with 4 digits 9,999. On the other hand, in binary, using those 8 bits, if we turn them all on, the largest number we'd get is 255. We as humans have a difficult time working with all the digits in the binary system, but a computer that can process instructions at a rate of a couple of billion instructions a second would have no problem. Why don't we take another look at a binary number and see how to convert that to decimal? Here we have the binary number 100101110 reading from right to left. We would like to convert this to decimal. I've always found it simple to put the position values across the top like this when I'm trying to do one of these conversions. It's very easy to do. Then place the binary digits to be converted right underneath those position values. Since the value of each bit is its own value times the value of its position, this really couldn't be easier. Since 0 times anything is 0, all we have to do is add the bits that are turned on or have a value of 1. The 128-bit is turned off, so we'll just skip it. 64 is turned on, so we'll just write it down. 32 is turned on, we'll write that down. 16 is turned off, so we'll ignore it. 8 is turned on, so we'll write it down. 4 and 2 are both turned off, so we'll ignore them, and 1 is turned on, and there you have it. Those are the bits that are turned on. We just add those values together. So here you see the decimal equivalent of this binary number. That was pretty simple, don't you think? Now, what if we wanted to convert in the other direction? Decimal to binary. How would we do that? Let's take decimal 156. Can we subtract 128 from 156 and get a value of 0 or greater? Well, yes, we can. So let's turn that one on and do a little arithmetic. 156 minus 128 leaves us with 28. Can we subtract 64 from 28 and get a 0 or higher? No, we cannot. So we'll just put a 0 there. Can we subtract 32 from 28 and get a 0 or higher? No, we cannot. So we'll just put a 0 there. Can we subtract 16 from 28 and get a 0 or higher? Well, yes, we can. So we'll turn it on, do a little arithmetic. 8 can come out of 12 and get a 0 or higher, so we'll turn it on and do a little arithmetic, which leaves us with 4. And sure enough, 4 can be taken from 4 and get a 0 or higher, so we'll turn it on. Leaves us with 0, so we'll just set the last 2 digits to 0, and there you have the binary equivalent of decimal 156. If you want to confirm that, just add up the bits that are turned on. So there you have it. That's how you convert binary to decimal and decimal to binary. But what does all this binary business have to do with computer data? Actually, binary bits are really used with a coding system to represent data. Here's an example of the most common binary coding system, Ascii. Notice the labels at the top of each column identifies a data type. The first column is decimal, a decimal number, and hexadecimal, and you go on, and out here you see character data type. If you take a look at these that are highlighted, decimal 67 is a capital C. Decimal 97 is a lowercase a. And decimal 116 is a lowercase t. Let's examine this some more. If we were to type the word cat with an uppercase C, what would the computer be sending between its various components to represent that word? Here you see an excerpt from the Ascii table where we've plucked out the 67, 97, and 116. We already know that the computer uses binary, not decimal. So for that character to be sent, the 67 would have to be converted to binary. You can practice the method shown earlier in this video to find this out. When you do, you'll find that the 67 is that in binary. The 97 is that, and the 116 is that. So here you see what is transmitted between the components of the computer, this string of zeros and ones to represent the word cat with a capital C. Imagine what the string of bits would look like if you were transmitting a manuscript, downloading the Bible. That would be a tremendous number of zeros and ones, wouldn't it? If you were transmitting a video, a movie, or something like that, where a single pixel can take up as many as 30 bits, you would really have a massive document. You would really have a massive file. So, there's our discussion of the binary coding system. If you've already watched the software video, then now you can go out and take the coursework quiz on software and binary and the internet, and you're ready to go. Have a good day.